And we're streaming now. Streaming now. Streaming now. That should be working. Pardon? No. He's actually gone home for medical reasons. So, not at the moment. Oh, it should be just at the back or at the front. Hold it. It's right here. Anybody else who wasn't here last year? Okay. What we did last day, the instructions are written on the next page. Assuming all percents are in grams, convert each element to moles. Write the formula using the number of moles as a subscript, divide it all by the small so that you have those instructions. Because I know sometimes these explanations, we did it, but it's handy to have a written reference. Today, we're going to do the second part of empirical molecular formula, which is, of course, molecular formula. And molecular formula is related to the empirical in that they can both be the same, but it's possible for the molecular formula to be a multiple of it. So if you had a carbohydrate, the reason, can anybody give me an example of a formula of a carbohydrate from biology class? Anybody here in AP Biology 12, 11? 11, I think you do the biochemistry. No? Yeah, yeah. Have you done the biochemistry?
I don't know. I've missed a lot of classes.
Did they do carbohydrates?
Yeah, we touched on it like briefly. It was sort of like we did a research project about it, so we just did it ourselves.
Oh.
So there's little pieces of it that are like missing.
Fair enough, fair enough. Did they tell you the formula for a carbohydrate?
Probably.
Does it? I'll approach this a different way. Does anybody know the formula for sugar? Yes?
C12, C22O11.
C, glucose.
C6H12.
The reason I say that is because you've given me the accurate one, which turns out won't be exactly what I want. It's technically true, because you lose it in dehydration synthesis. This is a molecular formula. The empirical formula, and the one we calculate with the previous method, is the simplest of all possible formulas. C, if I just make this C1, what is the rest of it? H2O. And that's why carbohydrates are known as carbohydrates. They are a carbon with water. They're not. It's not like they're made of water. I mean, they kind of are. But only linking do we get dehydration synthesis and things of that nature if you're in biology. But if you look at the simplest formula, it looks like the formula for water. So carbohydrate. Now yours that if we were to double this, we would get C12H24O12. And for often biology 12, that's good enough for me to say, oh, that's also a carbohydrate. But what's the formula you gave me?
C12H22O11.
Yeah, it is. The reason being is every time you join one of those, you lose a water, so you lose an H2O. So that's the accurate formula. And we often ignore that and we just write that because it's doubled. It's good enough for biology 12 usually. If we were to have, since it's Christmas time, that could be the empirical formula, ho ho ho, Santa Claus. The actual molecular formula may turn out to be H2O2, and that's the only version that exists. There is no H3O3. This is the real formula, and this is just the simplest version. Now I've run out of my room, and I wanted to do another example, so this is going to be annoying. Sorry, because I'm going to do that. If we have the formula NaCl, its other formulas is NaCl. The empirical formula and the ionic formula are the same, and they don't change. Theoretically, if you had a crystal, it would be 3 million Cl, 3 million, until you can finally get to the size you can actually see a single crystal of NaCl. Speaking of seeing a single crystal, someone just won a photography award for taking a picture of an atom with a regular camera. He has it hovering in like a little magnetic area between two magnets that are 2 millimeters apart, and it fluoresces under enough light. So under a certain wavelength, it gives off light. So he fluoresced it and then had a camera there under a super long exposure and was able to get a picture of the light coming off. So he took a picture of an atom, a single atom.
Can you see the picture on it?
Yeah. Yeah, now that I mentioned it, I'm like, I should have had this ready to go, but I only just found out about it yesterday. Picture of a single atom award. Ooh. Photograph of a single strontium atom wins national award. Let's go, let's go, let's go. No, I don't, okay. No, I don't want to enter my email. Oh, you're annoying. 1 second. I'll just do that. Instead of taking the book. So there's the picture. I don't want to visit because then they ask me for my email. But that little dot right there, that's the atom. And that's about 2 millimeters apart. And so he fluoresced it and left the camera there to expose it long enough that it gathered enough light.
What atom is that?
Strontium. Strontium. See if I can get, petapixel. Oh, and I just noticed, I said recent. I heard about it yesterday. I just noticed that says 2018. So it was recent to me. There we go. Anyway, I thought that was really cool. Gives the total number of each kind of atom in a molecule. Ionic compounds only have empirical formulas. You have to be given the molar mass and the empirical formula to solve. We can calculate this. So with last day's work, we know how to calculate the empirical formula, but you have to be given its molar mass. Now, in practice, we can do that because we will figure out from the percent compositions the empirical formula, and then we get the molar mass from a special machine. We throw chunks of the stuff into a machine, and then the machine takes your sample and flings pieces of it against the wall. And as it's flinging pieces of it against the wall, it has to go through an electric field. We usually charge the particles, and so it will deflect them, and it will deflect the ones that weigh more or less. And you get all these peaks of all these different masses. The one with the highest peak is usually the ones of the actual formula, because there's lots of that, and that turns out to be the molecular mass. So we have a machine that will actually just, you plug it in, and it gives you that. If I told you, did I tell you the other day about the guy who cost the company $5 million? He broke the light bulb for this machine twice as well. Each light bulb once cost $500. He put it down on a table and they just rolled off. Smashed it. I worked at a company in which essentially we determined things like percent composition and empirical formula. It was for a mining company. So last day when we were doing this part, what is the percent composition of each? Oh, not that part, sorry. What is the percent of water in there? I had a job for an entire summer where that's all I did. I didn't actually do it. I took a sample, I put it into a crucible, and then I put it into a machine. And the machine analyzed it, displayed a graph, and then I, with all my vast chemical knowledge, went, that looks like a good graph. And I accepted the result, and I wrote it down, and I signed my name to it, and sent it off to the entire refining part of the plant. One night, I wasn't working. I just want to be clear, this wasn't me. A result came in that was really weird. So they analyzed the sample, they looked at the graph, and they went, yeah, it's fine, and they sent it on. The plant, phoned back and said, are you sure that result is right? And he's like, yeah, sure, it's fine. So they did the plant, It was the wrong number. And so everything got contaminated because you adjust the plant to the amount that's coming in. They had to shut the entire plant down for 2 weeks while they cleaned it. Cost the company $5 million. And all because one person put their name next to a number that was clearly and obviously wrong. They didn't get fired though. You can't actually fire someone just for simple mistakes. They're probably never going to get promoted. But they don't seem, they did break 2 light bulbs and they didn't seem to care. But they didn't put them on that job ever again. Okay. Let's do an actual problem. Let's do instructions again. Forget that. The empirical formula is this. We know the molecular mass is that. What's the molecular formula? So, you can figure out the actual formula with just those numbers. Put you into a little. We are chemistry E. There we go. Do that on the board. Write down numbers, see if you can figure out what you have to do. Find those people. Go to the board. I want to see if everyone's working on the board. First group to get it wins a prize based on C. Okay, write down all the things you can about that. See if we can figure out how to do that. Good numbers. What's the molecular formula? Yeah. You guys good? Go forth. Help other groups. Who's winning? Once your group gets it, have a seat. Okay. Once one group had the light bulb go off, after that, it usually spreads fairly quickly. It's noticing as you're doing this that the molecular formula looks an awful lot like it's exactly double the empirical formula. So we know the formula must be exactly double. They're in proportion, so we double the whole thing and it becomes N2O4. Does anybody still want to get that down? Yep, there's some people ready. I'll wait a second. In that case, someone will in a moment. If the empirical formula is CH2 and the molecular mass is 70, find the molecular formula. Renee, what's annoying you? You were making gestures like this and everything. Is it chemistry or is it soccer? Both. Next one, how do we start off with this?
So
14. So CH2, let's start off with that. That's 14 grams per mole. And also, I want to make sure just for we keep all the sig figs. Not that it matters too much in this particular case, but yeah, 14 grams per mole. And then what do you do?
And the other one is 70 grams.
Yeah.
Take 70 grams per mole over 14 grams per mole. Okay. Or just 70?
Yeah. 7 goes in that twice, goes in that 10.
Yeah,
So
exactly.
10 divided by 2. But fine. Final formula then would be
5, and then it is CH2 times 5, which is C5H.
probably a compound that looks like this. 1, 2, 3, 4. Oh, I forgot a carbon. And no. Oh, we've got the 2. Yeah, this is a cyclopentate. It'll have 2 hydrogens in each one. I was giving it too many double bonds. Yeah, this is a cyclopentate. Have you done some organic naming before? Yeah. I'll get into that at the end of the year. Compound that looks like that, C5H10. And so we would, if we just measure the percent composition, we're going to get CH2. That's not the real formula. We're going to need this process to get that one. So to use all our skills, you start at the beginning and you say, okay, a compound is 40% carbon, 6.7% hydrogen, and 53.5% oxygen. Its molecular mass is 180 grams per mole. Find both the empirical and molecular formula. Now, Jillian, you weren't here last time. So while everybody's busily getting started on that, what we did is you would assume for our particular compound here, because their percent composition by mass. So you can use any rock you want, but it'd be very convenient if you used a rock that was exactly 100 grams. So in the one we did the other day, it's 70% iron and the rest is oxygen, so 30% iron. So instead of taking that percent, you go, well, I'm going to pretend I'm using 100 grams, and then we'll go 70 grams, because 70% of 100 is grams, and divide by the molar mass, you get the number of moles. 30 grams divided by the molar mass. Now you have a mole ratio, which is a formula. You can say that for every 1.25 of those, I've got 1.88 of those. But we need them in whole numbers. So you divide by the smallest one, and that at least gives us one whole number of 1. And usually the other one is a number that we can then use, like 1 or 2 or 3, or it's a number and a fraction that is really obvious as to what it should be. So if it's 1.5, that's 1.5. That tells us just double the whole thing, and we have the simplest whole number ratio. Okay?
So you're basically just changing the percentage
Into a formula. Yeah, so you turn it into moles and then turn it into a formula ratio. Yeah, there should be. Yeah. Oh, right. Last class we started off doing a multi-step mole problem on the whiteboards, and so that process isn't on there because people did it on the whiteboards, but you'll see the question. And then we started this process. Okay. Yeah, come around, just take a look. When we're ready, we'll go through how to do that. I need to see way more work. You got to use those numbers to show me that. Yeah, you need to prove it. Most of what you get marked on in Chem 11 is the communication part, which is showing all your work. The answer is like if you give me a question, like there was some people in the class who I called up because they were doing a calculator error, where if they didn't put the brackets in properly, they didn't use the special button for sending notation, they get completely the wrong answer. But all the work is perfect. That just takes you from an extending high to extending. But the answer is completely wrong. Oh, that's lovely. Right. So what did you do with it before? Like, yeah, so now you should get what the equivalent of that. Yeah. Yeah. And then you're up and doing it, right? Oh, you've got like C40, B6.7. What do you do with it before that? Yes, yes, so you have to do that for each one. Yeah, yeah, yeah. Oh, yeah, I can see that. Yeah, yeah. And then what do you do? Not yet. Yeah, you have to finish the empirical section. So, if I go all the way back to the instructions, what I'm looking for is, and I'll put the not the method, but here. So you assumed all percents in grams, you converted each element into moles. You've written the formula using the moles as subscript. How do you divide them all by the smallest one? So do that, and you'll get whole numbers. Yes, except weirdly you put hydrogen first, but I would be forced to mark it right as much as it would thoroughly pay me to do so. Because carbon is always first. So you 96. Where'd you get 96? So you took 180 divided by what? No. Ignore that number. The first thing you do is from the percent compositions, find the empirical formula. Like the exact same method as last day. You don't use this at all. No. Yep. And you get that. That's from the invention systems.
Yeah, and then, but I'm just wondering, multiply all subscripts by the same number to get the smallest prime number.
Remember last time we got like F10 1.5.
Yeah.
So we can multiply by 2 to get
To get
2, 3.
the whole
Yeah. But if they're all already the whole number, then you know.
Why don't you get like a 1.01?
Well, that's 1.
Rounded up, yeah.
1. It's 1 with an experimental error. Yeah. Remember, 2 plus 2 equals 5. We're very much trying to do 2. You can upstart your hand. That's the only one.
Is it this stuff?
Yeah. I've updated the method as to where we are. Yeah. And that's, yeah, remember to include units, like it's 30 grams per mole. And then 180. Yeah. 180 divided by 30 gives us 6. And then you multiply, yeah, so you've got the empirical and the molecular. Yep. Yep, because that is 1 with an experimental error. It's always plus or minus 1 in the last digit. So 3.34 is exactly the same as 3.34. Excellent. And so that would write down the formula. That would be CH perfect. And then you take, and then you get the molar mass of that, which is right. And then you have to show how did you what did you do that? Perfect. And then you get, oh, look, you show your work. Oh, beautiful. Now, I honestly, the way you were doing it with the percent and you go into the thing, if you show your work step by step of that, I would be like, that is right, then I'll mark it right. But you can't do it in your head, you would have to show it step by step. But the reason I also want you to do it the other way is you will get some types of questions in which you can't do that. And so I want you to make sure you do the method as well. I don't think I've checked here. You guys are looking. 180 divided by 102. 122. What's the molecular mass of CH2? Where'd you get it from? Oh, yeah, you don't need to. This part looks good, and then you divide by them all to get that, you know, that is together. And then you just get what is the molar mass of that? Oh, okay. And then you divide that into 180. Yeah, whatever that turns out to be. Once you're done, You can start working on Hebden. The Hebden has been updated with the empirical molecular formula sections. Yeah, sure. Given that most people have it, I'm just going to write the example on the board and you can double check it. Oh, so for that one, what we did is you need to, another percent, you need to divide something into the total amount, right? So the total, what is the total amount of H2SO4? Oh, yeah. And so then you would do it like H2. So, where did we have it? No. There we go. So the molar mass of H2SO4 is 98.1. And so the amount from H2 is 2. The amount from S is 32.1. 4 oxygens is 16 times 4 is 64. And then we would get a percent for all of those. Does that make sense? Now, do you want me to stay here, or are you gonna try and work it out?
Yeah.
Try and work it out. I can flip back to here, and then I will just write out the example here. Yes. Yeah, it's the simplest version. That's all it is. Yeah. I made that messy. What? No. 3 goes in 186. So to check your own work, taking each of the percent compositions, dividing by the molar masses to get the number of moles, put those into a formula, divide by the smallest ratio here, 3.33. You'll get CH2O. CH2O is 30 grams per mole. Divide that into 180. So you don't use the 180 until the very end. There is actually a way to use it to get the answer. That's what Ryan kept trying to do, and I kept trying to smack him in the back of the head to stop. But there are times in which you can't do it that way, so I wanted to make sure you can do it both. But if you did that on a test, if you figured that out and you go, oh, wait, I've got the percents and I've got that, I can figure that out. Obviously, if you show all your work and do the math, that would be worth full marks. It would be fine. Divided into it, though, you get 6. So it is 6 times larger, C6H12O6. You have so in terms of Hebden, we are all the way up to here, empirical molecular formula, down from the mole summary. We are about to start concentration, and then we're probably going to have a test, which would be probably a good idea if we had it before, so that you would remember. And today is the 2nd. And then give sufficient time for all those. This is block E. Excellent. December 12th. Test. Moles. Empirical formula. Chemistry 11. Should be block E. December. That's a week from today. What? That can't be true. What's today? What's today? Yeah, it's not a week from today. This thing's crazy. So today's the 2nd. We get all next week. Great. Actually, that's perfect. I will probably be able to finish the concentration section. Nice. It is Monday, December 12th. It is on a Monday, but that makes sure it's not on like the last day. I can look it up. That will be first block on Monday. Yes.
Will this just be covering unit 4 and unit 3?
So this will be covering only this section. Now, there's a warning with that, though. If you're answering a question in this section, do sig figs matter?
No.
Yes. Yes, they do. And if I say you have to figure out the empirical formula of the molecular formula of aluminum chloride or something, do you have to be able to know the formula of aluminum chloride? Yeah, you do need to know the formula of aluminum chloride. If I do something weird. Well, no, it is ionic. But I could say calculate the percent composition in copper 2 sulfate pentahydrate, in which case you have to know nomenclature. So I'm not going to directly test you on it. It's just already embedded in all the other questions. Yeah. What color should unit 1 be? I think a purple. Unit 2, make it hot pink. Unit 3, black. It's foundational. Unit 4, red because it's Christmas and that's actually on your test. Thank you.
Thank you.
Thank you. Thank you. Mm. Mm.